There we go. So the stream should be on in a few seconds. There's a lag time between, I guess, 5 to 10 seconds ish. It should be on now. Yes, I can see the live stream is on at this point. But if you try to watch the the voice chat on Discord, that should be working already. Yeah, so people who cannot hear me, you can check to make sure your deafen icon is not active. There's no bar across it. So the icon that looks like a headphone, that's your deafen icon. If there's a red line across it, that means you have deafened yourself, so you won't be able to hear me. Okay, so if it says maximum number of viewers has been reached, then go ahead and use the YouTube link, which is at the top of this particular text channel, because I pinned it. Pretty sure I did. Let me check.
No, you have not yet.
I have not. Okay, but it's at the top. So pinning it makes it easier because now you can go to the little thumbtack thing at the top, and then just click on that. So let me just type that here. Thank you. Oh, somebody just repeated that down here. Thank you. Thank you, Nathan.
Do you have a bot to create your text channels, or are you doing that manually?
It's simple enough that I can just do it manually. But I did write a bot, for Discord. It's actually pretty fun to do. And I didn't use any existing, npm module for Discord. So I basically wrote the entire thing out of very simple HTTP requests. That is the sort of thing that I like to do. And I think it's almost time, if not already time. Oh, my goodness, it's 2 minutes or past the start time already. So the first thing I want to do is to really kind of talk about some of the concerns or questions from the previous lecture of why are we talking about transistors. Okay, there are a few reasons. Okay, there are a few things, a few factors driving why I talk about this. So the first one is many years ago, when I taught this class, I was teaching it like everybody else. Okay, I was teaching the x86 instruction set, and I found that to be very difficult. Most people associate the operations of the instructions of the opcodes with the syntax of the opcodes. So most people think, oh, if I put parentheses around this is dereferencing, and if I don't, it is not dereferencing. And it is because of the parentheses that is making this happen. But in reality, that is not the case. Okay, because parentheses are not, that's just the syntax. It's the underlying implementation of the instructions, how things operate in the processor and how the processor work with RAM that makes certain things happen. So without getting down to that level and explaining things down to that level, people get confused because the syntax of assembly language can be very confusing. Okay, especially when you're dealing with a CISC architecture like the Intel x86 architecture, and that can get super confusing. And most of that confusion is unnecessary. Okay, because you are unlikely to have to program things using the x86 instruction set because tons of compilers are out there for that particular architecture already. So the purpose of this class is not so much that you will be programming in assembly, but to give you the under the hood view of what happens when you run a program in C. Okay, that's one objective. The other objective is for people who want to get into computer engineering or electrical engineering, where those people want to get into the design of the next generation of processors or GPUs. Okay, GPUs, you can kind of look at those as as highly special purposed processors. Okay, they are not general purpose processors, but they are still processors of sort. Okay, so they have a similar architecture when you compare that to a general purpose processor, except they get special devices, to carry certain operations in a very with high efficiency. So I want this class to give those people who want to design the inside of a processor, a head start. But I also want to give people who just want to program in C or C++ a head start when it comes to debugging a program. There are certain bugs that you can write in C or C++ where the symptom is unexplainable unless you know what is going on in RAM. So that's why that's what inspired me to teach this class the way that I currently teach it. But there's one more thing that is super selfish. It is myself, okay? Because I like to know how things work. That's just who I am, okay? I like to know how things work just for the sake of knowing how things work, okay? Not for any particular reason, okay? So when I look at a Nand gate, okay, I go like, well, okay, the Nand gate is really easy. It's really just an operator, okay. When it comes down to it, it's really equivalent to an operator, but it's done in hardware. But then I ask, how does it get it done? Okay, because we know computers are made out of lots and lots of transistors. Okay, but there are still transistors, which are fairly simple devices, especially when we look at it from the binary perspective. It's either on or off. Okay, now there's an entire branch of electrical engineering that deals with analog signals and analog devices. Now, in that particular area, transistors can be very complex devices because they're not considered binary devices anymore, which is really just on or off. But for us, a transistor is just a switch, okay? So my question to myself was, how can we make a NAND gate out of these really, really simple devices? So that's kind of why we started with transistors. So let me share my tablet screen so that I can kind of show you the progression of things from here on. Okay. All right. So here's a new page. Very good. So what we are doing right now is we are talking about transistors. Okay. And then from transistors, we are going to build gates. Okay. So this is the symbol of a NAND gate, and the NAND gate is essentially it's like a hardware operator. Okay, so a NAND gate then can be used to make an AND gate. It can be used to make an OR gate, and so on. And then these things in return will be used to implement addition. Okay, so that's a pretty interesting jump, because if you think about it, Boolean operations are fairly simple, right? You have taken CISP300 and 360 for sure, and we know how what Boolean operators are. So the question is, how do we bridge Boolean operators and arithmetic operations that we want a computer to do? So from OR gate, AND gate, and NOT gates, we want to make adders and also subtractors, because eventually these are the mechanisms that we use to actually do computation. Okay, the processor, when we refer to processing, a lot of the processing has to do with really just kind of adding, subtracting, and comparing. Now, yes, we can do multiplication, division, and all kinds of more complex math operations, but they can all be built upon adding and subtracting. So once we have adders and subtractors, then we talk about how things are memorized. Okay, so we talk about memory, and then somewhere in between we also talk about how values are represented. In other words, okay, this is going to sound odd. Okay, so look at the screen, right? How many fingers is up? Okay, that is a quantity. Okay, in your head, when I ask you the question, how many fingers are up, your answer internal to your mind is really just a concept. It is a quantity. Now, when you say 5 in English, that is a representation of that abstract concept, in terms of a quantity. So the question now is, well, the computer doesn't have 5 fingers, right? On a hand. how does a computer represent values? Okay, so that is what this piece is going to do is basically representation of values. And then we'll also talk about double precision floating point numbers. That's the full name of double. And doubles can be used to represent really small quantities and really large quantities. Okay, now it does not have high precision. Okay, it has less precision compared to 64-bit integers, but sacrificing precision, it has a larger range of values that it can represent. So we'll be talking about that a little bit as well. But eventually, we will get to this portion here, and we'll be starting to talk about how a computer can maintain data using basically gates, okay, which boils down to transistors. Okay, so after that, okay, we got the adder, we got the memory, we got some other kind of hodgepodge of devices. They're all fairly simple devices. Then we'll actually get to the point where we'll talk about the processor. Okay, the processor is kind of like an orchestra. Okay, you have basically different sections of the processor doing different things. Okay, so you need a conductor to coordinate all of those different components inside the processor so that they get certain things done in the right order, okay, so that these components can kind of cooperate and coordinate with each other. So from that, okay, we talk about opcodes. Okay, basically how does the processor know what to do? Okay, those that's specified by opcodes, but then opcodes get translated into microcodes. Okay, and then when we get to that point, hopefully it will be clear what those things are, and then from opcodes we'll get to basically how do we translate C to opcodes. Okay, so we'll become organic compilers. Okay, that's about, I would say, about midway through the semester. We'll start to talk about opcodes and actual programming using quote unquote assembly language. Okay, so okay, I'll just put a slash assembly language here, and this is a big deal because this translates to what about the control structures. So how do we implement conditional statements? How do we implement loops like while loops and do loops? How do we call a function? And in a function, how do we return back to the caller? Blah, 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 blah. Okay? And then we also will talk about local variables and parameters. How do we pass parameters from a caller to a callee? How do we specify return values? Okay, you have a return statement and it has an expression. So how does that value become known to the caller? Okay, so all of these mechanisms will be talked about, and then we'll talk about pointers. Okay, you have pointers in C and C++. We'll talk about arrays. And potentially, okay, depending on how much time we have, we might even get into structures. Now, structures in this case, they're called structs in C. They are basically the precursor of classes. Okay, so we're going to be talking about constructs that has members, data members. We won't get into actual classes because I don't want to get into methods, because that's a little bit complex, from the perspective of assembly language. So I would avoid, doing that. And then when you combine all of these things, we will be implementing recursive algorithms. Okay, because I think one of the things in the other classes like CISP360, 400, and even 430 is even though recursion is a concept that is introduced, many people may be kind of a little bit baffled by, so what is going on, right? There's only one function and it's calling itself multiple times. So how does it keep track of things like local variables and parameters and stuff like that? So by the time we get to recursive algorithms and we implement the recursive algorithms using assembly language, and we'll be able to see how it utilizes memory, basically the stack, to keep track of everything. So hopefully that will give you an insight, okay, of things that you might have learned already or things that you will learn in other classes that involves recursion, structures, pointers, and stuff like that. So this class, eventually, hopefully, will give you a very low level but essential deep understanding of concepts that other classes would also utilize. So I hope this kind of gives you a general map, of what we are going to do in this class. So do we have any questions or any discussions related to what I just said? Go ahead.
Yeah, I have a quick question.
Yeah, go ahead.
So I just want to make sure I understand this. Are gates just a way for you to utilize booleans to interact with the processor then?
A gate is basically a hardware Boolean operator.
Okay.
That's it.
That's it. Okay.
That is it. So instead of so the two sides of of an operator that has a left hand side and a right hand side, we just have two wires coming into that gate, and then the result of an operator, which then can be used for another operator, that becomes the output of a gate.
Okay. Gotcha.
All
Thank you.
right. Absolutely. Any other questions? Any other things that you guys want to talk about based on what I just said? Nobody? No questions? All right. Cool. All right. So what I am going to do then is to hide the tablet, and then we'll continue with our discussion of physical states and stuff like that. And what we'll do today is to continue with the circuitry that we were talking about. Oh, by the way, I finished grading that assignment. Yes. For those of you who know me, I have a bad habit of procrastinating, but I didn't procrastinate this time. So I'm hoping that I can overcome that tendency and get things graded earlier and sooner. Okay, but anyway, I got it graded, and most people got perfect scores. Okay, they did all the multiple choice tests. They're done right. I mean, it allows an infinite number of retries. Okay, within the time of the lab, so most people can get that part. And then for the part where people have to turn in the circuit, most people got perfect scores, and some people did not follow the instructions. Okay, so a few people did not follow instructions. A few people made some mistakes, and the mistakes. Okay, let me just kind of zoom in here so I can tell you what the mistakes are. So some people copied this diagram, but the lab actually wants to use a 8-bit input, 2 8-bit inputs, and 1 8-bit output. And some people did not do that, did not follow the instructions of the lab. Okay, a few other people, kind of pointed the transistors in the wrong direction, so it did not work entirely. Let me see what else. I think those are the two most common problems with the submissions. So within the 5 points allocated to the actual circuit, most people got perfect scores, and then I would say maybe about 1/4 of the people, got partial credit, and then a few people didn't turn in anything. So obviously they got zeros for that. All right. I'm pretty sure the instructions are sufficient because most people did it correctly. All right. So let's move on, and let me zoom back out. Control 0 to go back to the original zoom level. And now we can continue to talk about what does it do. Okay, well, I mean, we kind of talked about it already because somebody already mentioned that this is a Nand gate. I'm just kind of tracking the Okay, all right. So so when you have two zeros as presented as the input, then the two top Q1 and Q2 will turn on, which means they connect. So now from the output pin's perspective, it has two paths to go to the high voltage, and that's why the output pin is going to register as a 1. Okay. Now, what about the two transistors down here? They're both off. Why are they both off? Because the source and the gate have the same signal. They have the same voltage, and that's how you turn off a transistor. So you just have to remember 0, 0 leads to a 1. Next diagram. What if your two inputs are ones? Well, if you have two ones as the inputs, then the bottom two transistors will turn on, and then the top two transistors will turn off. From the perspective of the output pin, it has a connection to ground at this time, and that's why the output is going to register as a 0. So as far as from the logical perspective, we now understand that, oh, okay, if the inputs are both ones, then we have an output of a 0. And the only case when it is a little bit interesting is what if we have 1, 1, and 1, 0. Okay? And it doesn't really matter which one is a 1 and which one is a 0 because it is symmetric in a way. So we'll just say that x is 1 this time and y is 0, in the same example. So what is going to happen? Q1 is turned off because Q1 now has the gate being a 1, but its source is also a 1, so Q1 is turned off. But Q2 is turned on because it has the source being a 1, but the gate is, track it down, is a 0. So Q2 is on. What about Q3? So Q3 is kind of a curious one because because its source is actually not connected to anything in this case, but we know this is an N-type transistor because because of the lack of a little bubble here. So for N transistors, the source can only be a negative or 0, and yet at the same time, the input to the gate is a 1. So we know this transistor is quote unquote on. Okay, but that's okay because when we track down input Y and also Q4, we know that Q4 is going to be off. And because Q3 and Q4 are connected in series, so if at least one of them is off, the connection from the output pin to ground is broken. So that's why in this case, the output pin has one single connection connected to the power, and it has none connecting to the ground. And that is why the output is going to register as a 1. So do we have any questions about this particular example? Why, when the input is 1, 0, the output is also a 1?
Yeah, Professor, I have a quick question.
Go ahead.
So when you talk about it being connected, can you just review again what qualifies the output pin to be connected to something?
So it has to do with whether a transistor is allowing flow or whether it is closing the circuit. So this was a discussion from Tuesday where I said, when the source and the gate of a transistor are opposite, the transistor is turned on, which means it is allowing flow from the source to the drain. When the source and the gate are the same, then the transistor is considered turned off, and that means it is disconnecting the source from the drain. Is that okay? I mean, does that help explain, when a transistor is on and when a transistor is off?
Yeah, thank you.
Professor, can you hear me?
Yes, I can.
Okay. I was just wondering if we were to put Q3 and Q4 parallel and Q1 and Q2 in a sequence, would that be essentially the same?
That is an interesting question. I have not considered that. It would not be the same, I believe, if I had to guess. Okay, this is definitely not a very good approach of doing things. But if I had to guess, that would make a NOR gate. instead of a NAND gate, it would be a NOR gate or negated OR gate.
Huh.
Well, let's go ahead and find out. Okay, this is the reason why the timing of topics is unpredictable, because some of you have very good questions that I really want to answer, but I don't have the answer right away. So let's work this out. And I think this is actually from a certain perspective, I think this is actually a very useful portion of the class where I show you how I work on problems, because I would try my best to explain how I think and how I figure out things. Okay, and then some people would say, but that's not in the syllabus, it's not in the schedule, it's not even in the curriculum, you should not talk about stuff like that. Well, I mean, if the stuff that is in the curriculum is important, but at the end of the day, at the end of this, not just the day, the semester, this is the toy processor, okay? No one out there is actually using this architecture. But it is the concept that you're learning that is going to be important. But the concepts is important, but if you can manage to kind of think and solve problems, if I can teach you that, okay, I think that is even more helpful, okay? Alright, so let's go ahead and think about the circuit. So we have 2 P transistors up here, right? So these two are P transistors, and then we have 2 N transistors down here, like so. Alright, there you go, and there we go. And then we have a similar connection where 2 of these connect to X as an input pin, and then the other 2, so namely this one and this one, would connect to Y. So I'm going to make these dots here to make sure that I emphasize which ones are actually connected and which one is not connected. And then the output is still going to be tapped from here. So this is our output. Alright, so let's try to figure out what's going to happen here. So we'll say, what about, okay, we got X, we got Y, we got the output. So when X is a 0, Y is a 0, what is going to be the output? So in this case, okay, the cool thing about using a tablet is I can use different layers. So this way I can erase stuff from a certain layer and keep the other one around. And obviously I'm not super proficient yet with this stuff, but we'll try to get this to work. Okay, there we go. So now I'm drawing on a different layer. Alright, so when X is a 0 and Y is a 0, we know both of these transistors are on, because this is going to be on, this one's going to be on, and then we know both of these are off, so the output is going to be a 1. So is that okay? Does everybody understand how I just figure out if both inputs are zeros, the output is going to be a 1?
Right.
Okay, very good.
Yep.
And I'm just looking at the text channel. Are the inputs like switches? No, the inputs are kind of like it's really just somebody either connects a terminal to the positive end of a battery or the negative end of a battery. That's basically what the inputs are. They are basically yeah, go ahead.
Is it possible to draw the wires in color to see how it's going, where?
I'm laughing because let me show you what the tablet looks like. Okay, and this is my remarkable tablet. It has no colors. It is a black and white device, and that is why I like it, because it uses e-ink technology, which basically means I can charge it and use it for days before I have to charge it again. But it's an e-ink device. It has no color, and I know it is being projected onto a computer which is capable of color output, but because the device doesn't have any way to specify a color, there's no way for me to draw colored lines. Sorry. I can use different thickness though, so I can try that. So I can use a thick line to indicate the flow. So from the
Gray.
I can do gray.
You
I
said
can
gray.
yeah, I can do that. Okay, so let me go back to the medium thickness and then use a gray color. There we go. So in this case, we start from the output pin. So we go to this junction here, and this junction says, hey, we got a path going to the positive end of the voltage. So that's why we follow this, okay, and then we have a connection to power or positive, and that's why the output is registered as a 1. Is that okay? Does that help?
Similar to like charging capacity, like when you see like a capacitor charging, and then when it's connected just to power, and then when you close the switch, then no electricity goes to the capacitor, instead it goes to the ground.
It's not so much a capacity. This thing is just really kind of hooked up to a voltmeter.
Mm-hmm.
Yep. So it's not really a capacitor. In fact, we don't want it to be hooked up to a capacitor because then it needs time to change its state.
Mm-hmm.
All right. That's kind of what it is, but it is really hooked up to a multimeter where one end connects to here and then the other end always hooks up to the ground because that's the reference.
Oh, okay.
And then we got are the input like switches? And the answer is no. The inputs are more like are we hooking up X to the negative end of a battery or the positive end of the battery. All right. So now this is all getting recorded on YouTube, right? Yeah. So I'm gonna erase this and then go to the next state. We got a few questions coming in, so I'm gonna see what the question is. No, we are not. We don't really care about flow. We just want to know which side the output pin is connected to. Is it connected to power, or is it connected to ground? So it's not exactly a flow thing. Yeah, go ahead.
Can I share my perspective on like how I'm interpreting it, if it might help?
Yeah, go ahead.
So I'm imagining like if you're looking at a computer and you have a processor, the inputs are basically like if you have a wire connected to it, whether or not it has electricity coming in, and the output has a wire connected out, and it's whether or not it has electricity coming out, right?
Correct. So the output is not necessarily connected to anything at all. We just want to know, what type of voltage would we experience if we were to touch it.
Could I ask a question real quick?
Yeah.
I just want to clarify. Are both of those P-type, or is one P and one...
On the top, they're both P-types.
Oh, okay. Gotcha.
So on the top,
Okay,
we
cool.
got P and the P, and then below that, we got the N and the N down here. And
Gotcha.
we got
Thank
sure, yeah, we got a question in the text. So in this diagram, X is controlling whether two transistors are letting a signal through. Not quite. X is really just an input pin. In other words, that's a place where you can apply either a 1 or a 0 from outside. And so is Y. So that's basically what an input pin is. It really is just a terminal so that you can say, I'm going to hook it up to the positive end of a battery or the negative end of a battery. Now, where it connects to, which gate it connects to in terms of the transistor, that influences, how X and Y would control the states of the transistors, whether the transistor is closing the circuit or whether it is opening the circuit. All right, so are we good so far with this diagram? Because if it is good, then we can move on to X is 1 and Y is 0.
Tack, I found
Yeah.
a workaround with the screen share.
Okay.
You left screen share on for students, so I'm just screen sharing your screen share. So if there's anyone else in here who wants to try to get a less or a more live feed, that might be a workaround for you guys.
But isn't that still going through the same voice channel?
Yes, but I believe it's 50 per screen, right?
Oh, so we can have more than 50
Yeah.
per voice channel?
Yeah. So
Yeah.
essentially,
So
we'd have
piggybacking
essentially
it
100.
is working for me.
Cool. Oh,
Aha.
this is
Nice.
interesting because this can go exponential, and then fan out is 50.
All right. Well, I think we covered the entire class.
So with
The only
two-
interesting thing here is I have to mute the professor because otherwise it's doubling up.
yes, is that going to be a problem for you?
No, I just have you muted.
Okay, gotcha. All right. We have a max per screen share. So if you are trying to look at my screen share and it says it's at the cap, then you want to go to Aaron's screen share because his screen share probably is at a very low capacity. So people who are watching this through YouTube right now because you couldn't get onto my screen share, you can go ahead and try to see if you can get onto Aaron's screen share. Yep. Yep, that's big brain stuff. This is what I'm talking about. Like how do you solve a problem, right? What tools do we have? And I did not know that you can reshare a screen. So so that tool was not. I didn't make that connection. Okay, I probably should know that there's a way to. You couldn't get onto my screen share. You can go ahead. Oh, that was me. Cool. All right. All right. So getting back to the circuit diagram. So now I'm gonna delete layer 2 so that we can go back to the blanks the original configuration. So we can still put something here. Okay, we can still right. Okay. So now we get back to the medium but black line. So we know the output is 1 in this case. So now we want to figure out what if x is 0 and y is 1. Okay, this is what we want to figure out now. And well, this chord actually only had a max of 25 before, and then you also need booster, and it needs to be paid in order to have more people to watch the video screen share, and they made it free because of COVID-19. So of all the companies, I think Discord is one of the more community minded type of companies, or at least at this point there's evidence suggesting that. Alright, so we're going to add a new layer again, and then we'll change the color to gray so that I can draw some connections. Alright, so at this point we know that x has a 0. So x has a 0, so that means this is connecting. And we track down to this N transistor, so we know this one is not connecting, right? And then we track down y. Y has a value of 1. So that value of 1 is going to turn off this transistor, and it is going to turn on this transistor here. So now we want to look at things from the perspective of the output pin. So the output pin starts from here, and it goes to this junction, and it asks, okay, do we have a way to connect to ground? And it says, sure, there's one way to connect to ground. All right, so that is cool, but we are not done yet because we also want to make sure that it doesn't have a way to go to power, because if it does, then we have a problem, because you don't want power and ground to be connected to each other. Okay, so I'll let you guys sort out the share of a share screen.
Professor, I had a question.
Yes, go ahead.
So you're talking about the flow from the output pin goes to ground.
Right.
How do you know that? Can you clarify that for us?
Because okay, let me name these transistors, and that I want to be persistent, so I'm going to use layer 1 for that purpose. So we call this one Q1, call this one Q2, call this one Q3, call this one Q4. Okay. So from that perspective, Q4 is on, Q4 is connecting, and that is why when you track from the output pin, when we get to this junction point, Q4 is connecting. That's why we have a connection to ground. Is that okay?
Yep.
Okay. But we do not have a way to connect to power, because when we get from this point to this point here, we got disconnected right at this point. Q2 is already opening the circuit, so whether Q1 is on or not is actually not important, because if two transistors are connected in series and one is off, then the entire series is broken. It is not connecting. Is that okay?
Yes, thank you.
Sure. All right. So now the conclusion is this is going to experience a 0 here. So I'm going to delete layer 2, switch back to only layer 1, and then use black ink again. This is going to be a 0. So we can kind of, I'm going to skip this one because it is kind of symmetric in terms of the analysis that I just did. And then we'll move on to the last one, which is what if both inputs are 1s? And I think some of you kind of can work this out already by yourself. So if you can, that's good. If you cannot, that's okay too, because I want to show you how that is going to be done. So when both inputs are 1s, okay, so we have 1 and 1 here. So the 1, x going to Q1 is going to turn off Q1, which means Q1 is disconnecting. It is an open circuit. Same thing applies to Q2. It is also an open circuit. But because for N-type transistors, when the gate and the source are different, the transistor is turned on, so we know this is connecting and this is also connecting. So now when we analyze what the output is going to experience, so we now start with the output pin, and it goes to this junction point first, and it goes like, hey, I already have a path to go to ground. But we are not done yet. Just like the infomercial says, but wait, there's more. Because now, when it continues up to this point, it has a second path to connect to ground. So we can basically say it has a very, very good connection to ground. But nonetheless, okay, from the logical perspective, we just say, yep, it's connected to ground. So that's why we know that the output is also going to be a 0. So now, instead of cluttering the display, I'm going to take out layer 2, switch back to layer 1, and switch back to black ink. We just put a 0 down here. So now you look at this output and you ask, what kind of a gate is it? Very good. All right, so we got, no, that is conditional. That's implication. We are not dealing with implication, so scratch that from the text channel. Or you can just ignore that. Okay, you guys just ignore the truth table in the text channel. It is a correct truth table, but not for the circuit that we are making right now. Okay, so when you look at this output, then you remember I had a kind of like a gut feeling, that this is a NOR gate. So let's see if this is actually a NOR gate. Okay, so it is the negation of x or y. Okay, so when x is 0, y is 0, x or y is a 0, but the negation of that is a 1. When at least one of x or y is a 1, then x or y is going to be a 1. The negation of that is going to be a 0. That applies to all 3 rows down here. So now we can see the output and the negation of x or y, they are matching for every single row. So that's how we can see that this entire circuit is the NOR gate, which is basically the abbreviated term for negated OR gate. So I was right that my gut feeling was my guesstimate was actually correct. But this is good, right? We just kind of work through the logic to figure out that, oh, okay, so this is how we make a NOR gate instead of a NAND gate. All right, This is cool. Well, thank you for the question. Okay, I cannot remember who asked the question, but that was a very cool question because I enjoy answering questions like that. And let me check the text channel here. Okay. Alright, so I just got an suggestion of how we can get around the 50 max limit. And I do have a second account because I have a student account. And I can run the student account on inside the virtual machine. That would be awfully inefficient, but it is doable. So by next Tuesday, I probably would have experimented with that and see if it is a way to do it.
May I ask a question?
Yeah, go ahead.
Could you explain again how when x is 1 and y is 1, the output is 0? Because I was under the impression that because there's a connection to ground, that it would be 1.
Yes, we have two connections to ground in that case, because when x is 1, y is 1, then both Q3 and Q4 would connect. So that means we have two paths for the output pin to connect to ground.
So they just kind of cancel each other out? Is that
No, they don't cancel each other out.
Oh.
You just have two ways to connect to ground, which means we just have a very, very good connection to ground. That's basically what it boils down to.
So I guess the part I'm confused about is that when there is a connection to ground, that results in a 0 for the return value?
Well, when the output pin connects to ground, it is a 0. When the output pin connects to power, it is a 1.
Oh, I see. Okay. Thank you. I think I was switching the two.
Yep. All right. Cool. All right, so we got a bunch of stuff going on in the text channel, but I just took a quick glance and it seems like none of that, except for ground equals to 0, relates to the class discussion. I think I'll make a channel, like a side channel, so that non-class topic can go on to that channel, when I focus on the actual class stuff, using the date channel that we have here. All right. So
I was going to ask for something like that, but is it possible that you could do just quickly go over the NOR gate output with truth tables with the true or false instead? That would just help me understand it a little bit better.
Okay, so a 0 is a false and a 1 is a true. So we got the truth table right here.
Okay, that's good enough for me. Thank you.
Sure. Yeah, so 0 is false, 1 is true. I'm too lazy to write T and F because T has 2 strokes and F has 3 strokes, and both 0 and 1 is a 1-stroke thing. Talk about lazy. Yep. All right. So this is exciting. I like this. I like to solve problems and figure out how things work. All right, cool. But the bottom line, okay, so after this whole discussion, it basically tells us okay, using 4 transistors, just connecting them differently, we can end up with either a Nand gate, which is what is in the notes, or we can end up with a NOR gate, which is what we just talked about today. But the bottom line is we only need one of those, right? Because if you have a NAND gate, you can implement a NOT gate using a single NAND gate. So in this particular discussion, I just want to point out the symbols being used. The NAND operator, sometimes people use the up arrow to represent the NAND operator, which is kind of understandable because the mathematical symbol of NAND is kind of like an inverted V. But when you say not that, you basically have to put a stroke through it, and I guess in a certain way you can draw that as an up arrow. So if I only give you NAND and you have to implement logical NOT, this is how you do it. Okay, it's just X NAND X, x NAND x is not x. So do we have any questions about that? Does anyone want me to kind of show how that works? Or you guys are all good with that? Okay, we got one yes. Okay, so we'll go ahead and do it. Let me turn the tablet back on again. Okay, all right. So what we do is we make a truth table. Okay, so we got x here, we got x, we got not x, right? And then we have x NAND x. Okay, this is x NAND x, which is really the same thing as the negation of x and x. Okay, so we got 3 columns and 2 rows. Because we only got one single variable in this case, and x can either be true or false. Okay, so x can be false or true. When x is false, not x is true. When x is true, not x is false. So that part is pretty simple. Yes, so what Alfred is mentioning in the text channel is correct. A NOR gate can be described as the negation of an OR, and then the NAND gate would be the negation of an AND, which is described right here. Oh, it's behind the tablet. Let me just kind of show the screen here. So it is described here in the notes. Very good. There we go. So getting back onto the tablet, we want to figure out this part at this point. So now we want to say, okay, what is x and x? Well, in this case, x and x would be a 0, but the negation of that would be a 1. What if x is 1? X and x is going to be a 1, but the negation of that is going to be a 0, like that. So now we can see that the negation of x is really the same thing as the x NAND x. All right. So are we good so far with how I have just shown you that not x is x NAND x? All right. Yeah, absolutely. So now it is your turn to kind of work on this yourself. Okay, so consider this one of those ungraded assignments that I have talked about when I talked about the syllabus. I hope you guys have watched the syllabus video already at this point, because that's kind of important. But this is going to be an ungraded assignment, which means I'm not going to bother to grade. But I want you to go through the same mechanism to show yourself, okay, that x and y is indeed the same as x NAND y NAND x NAND y. Okay, so
Okay.
so I would let you guys do it. Okay, do it before next Tuesday. Okay. So you got quite a few days to work on this. Okay, but as you work on that, I think it will help you improve your understanding of the material that we are talking about. X or y eventually boils down to x NAND x. Oh, okay, sorry. So getting back to the browser. So x or y eventually boils down to x NAND x, the whole thing, NAND y NAND y, the whole thing. Okay, so I want you guys to kind of just use a truth table to work on this one, and basically show yourself, okay, show this to yourself that there is a equivalency between the OR operator and basically a hierarchy of the application of the NAND operator. Okay, so this is something that I want you guys to work on, kind of by yourselves, because I think it will be beneficial. So, but what is the bottom line? We just basically we were swimming in pine needles. Okay, yes, ouch. But where is the branch? Where's the branch? Where all of these needles are coming from? The bottom line is, we don't need a NOT gate. We don't need a AND gate. We don't need an OR gate, because we can do all of those using NAND gates. Okay, big deal. What is significant about that? Well, we know we can implement a NAND gate using 4 transistors. So if we can make AND gates out of NAND gates, if we can make OR gates out of NAND gates, and we can make NOT gates using NAND gates, that means all of those gates that we are familiar with can also be made out of transistors. That is the significance of this discussion. Okay, the logical operators, the Boolean operators that you are familiar with, can all be implemented using transistors. Now, I understand this is hardly surprising because we do have processors, right? I mean, we have processors running your C programs, which has Boolean operators, and so it should not be surprising. But when you're looking at it from the perspective of how do we make transistors, how do we use transistors to make up a computer, now we got the lowest level done, okay? Because now we have a way to use transistors to make the simplest gates that we are familiar with. All right? So that is the significance of this whole discussion, which started on Tuesday. So we move on to section 4, which is really short, okay? Because all it is saying is there is a difference between a number versus a value. So Nathan has typed something in the text channel, and the question is, are NAND gates kind of like axioms for all gates? So I think I understand what you're talking about, but the term that describes NAND gates is that it is complete. Okay, it is complete, meaning that it can be used to implement all of the other Boolean operators. But yes, but I'm so glad that Nathan mentioned this because that is what it is. Okay, the NAND gate can be used to implement all of the other Boolean operators. So section 4 talks about numbers and values because all it is saying is values are abstract concepts. Okay, how many fingers am I holding? That's a concept. Okay. Now, how would you call this quantity that is a number? Okay, so a number is a representation, of a value. And so, why do we need numbers? We need numbers because we need to communicate. Okay, so when you need to tell the other person, the quantity of something, then these two people, you and the other person, need to have a common understanding of, okay, what language are we going to use? Okay, what base are we going to use? And that is where numbers come in. Okay, so a number is a representation of a value, but the same value can be represented in a whole bunch of different numbers. Okay, so I'm going to give you an example. Okay, I'm just going to hold up something and ask, how much is it? Okay, how much is my pen? Some people will say, okay, it's $2. $2 what dollars? Okay, $2 US. Okay, fine. So now the next question is, yeah, I have no idea. I don't know how much it costs. Exactly. So we can change the unit. Okay, rubles. Okay, how many yens? Right? How many yuans? How many, euros? Okay, so the currency is kind of like different units, right? Because the same worth can now be expressed using different currencies. So that's the difference between a number versus the value the number is representing, is the worth of something versus what currency you are going to use to express it. Okay, you can even use, what is the weight of rice? Okay, how much is this pen worth in terms of grains of rice? Okay, you can even use that as a unit. All right. Well, that depends on who used that pen and where you sell it to. Cool. So now we're gonna move on. I'm looking at the time. Yeah, we got plenty. We got 20 minutes. So we're gonna move on. But before we move on, we'll talk about the lab that you'll be doing tonight. Yes, I know some people are dreading this. It's like, no, I would like to get off and have my dinner, not another lab. Well, this lab is called Nand 2, okay? But it's going to be, there's a reason why it's called Nand 2. Alright, so from your perspective, okay, this is kind of important because I don't want people to ask me again later. The access code is Nandroid. Yes, because the semester that I was making these questions, I was also teaching Android. I was also teaching Android programming, and it just go like, hey, I can combine these two. It becomes Nandroid. Yes, yes, Aaron got it right. Put it into the text channel. But yet, I'm pretty sure someone's gonna ask me later and go like, what is the access code again? Alright, so this is your quiz, or this is your lab. This is a pretty short lab, by the way, because we have already kind of talked about all of the concepts. What you have to do is to kind of do certain things in Logisim to basically experiment with all of these things and kind of look at Logisim as your lab, as in like a real lab, like a electronics lab, except everything is simulated. So if you accidentally connect power to ground, nothing is going to blow up, nothing is going to catch fire. It's all good, right? Logisim would just say, hey, this is not good. That's all you're going to get. Alright, so this is going to be due tonight, January 21st, and I'll give you guys up to 10 p.m. Okay, so that's plenty of time. I don't think you guys would need that much time. Yeah, you can probably find a lot of tutorials of Logisim on YouTube and other places too. And I'm pretty sure I'm not the only person who implemented a full processor using just Logisim. So you can go ahead and check out what other things people have done using Logisim, because it's really quite a useful educational tool. It turns to red. It's red because it is red hot, because it is hot. Don't touch it. There we go. Alright, so with that out of the way, so I'm gonna use the lab Nand2 as a role-taking mechanism. People who don't get it done by tonight will be considered absent in class, because I cannot really just kind of record everybody who's in the voice chat channel right now. It's already live. You should be able to click on it now. You cannot access the lab. It should be accessible by at this point. Oh, I can check that too. Oh yeah, refresh it. Yep. Okay, cool. I just need a confirmation that somebody is able to get in. And sometimes if Control R itself does not refresh, I found this the hard way. You can also use Control Shift R to refresh. Now Control R is a refresh already, but Control Shift R is a hard refresh. And sometimes, I don't know why, Control R itself does not sufficiently refresh, but Control Shift R would do it. Yeah, turn off your ad block. I have my ad blocks turned on, but I don't really have a problem with this. It may be I'm using Firefox and not Chrome. Okay, I'm not sure. Alright, so now we are moving on to base conversion. This is module 282. And this one talks about base conversion. And then you guys go like, oh no, not base conversion. Some of you may have some exposure to base conversion, and you might have learned something like this already in one of your other classes. But I think most people, have not learned how to do base conversion, not yet at this point. Okay, so we'll go ahead and diagnose the problem later, because I will stay online after the lecture to help you guys with the lab. So, so Zoe, we will address that problem after the lecture. All right. So getting back to values, numbers, and bases. Okay. How hard is base conversion? Okay, that's kind of the question. And the answer is, if you think you have enough education skill set, to work at McDonald's, you probably know base conversion already. Okay, so let me be a little bit more specific. Yeah, base conversion is easy stuff, man. You just have to look at it from a certain perspective. It is all about perspective. Okay, so let's go ahead and start with how do you make change, right? If you work at McDonald's. So I'm switching to the tablet right now because it's an example. So let's just say that you have to make change for I want to make this a little bit interesting. So let's say $17.69. Okay, there we go. All right, so this is the amount that you need to you need to come up with this amount while you're making change for a customer. Okay, at McDonald's or Safeway or whatever. Okay, and I don't want you to use 1,768 pennies, which is one way to do it. Okay, but I don't want you to do it that way because your employer and also your customer may not like that solution very much. Okay, and then the requirement is you have to use the least number of bills and coins to make up for this value. Does that sound like a difficult problem to you?
No.
Okay, and so most of us know how to do that, right? Okay, very good. So I'm glad to see that no one is saying, no, I don't know how to do this. Can you teach us how to do this? It's very good that I don't have to. Okay, that's very, very comforting to me. All right, but now you have to kind of ask yourself, how do you do this, right? How do you know that you need one $10 bill, you need one $5 bill, and I know that $2 bills exist, but you probably don't want to use a $2 bill, so we'll say two $1 bills, and then we have two quarters, right? And then we have one dime, we have one nickel, and then we got 4 pennies. After that, okay, there's a 0 here, and that should be the least number of coins and bills. So now the question is, how do we figure that out? Did I make a mistake somewhere? I think I did not make a mistake. Okay. Okay, we got Rachel typing in the text channel. Or not. Okay, so now the question is, what did you do? What did I do to come up with these numbers, right? So it really is a matter of division, okay? You try the largest amount first, okay, and then you try to divide the amount that you need to, the remaining amount, you divide it by, yeah, go ahead.
What do you have besides the 10 cent? Is that just a scratch mark or?
Where?
You have 2 times 20 cent or 25 cent, and then you have something times.
Yeah, that's a scratch.
10.
Oh, let me erase it. There we go. my stylus actually has an eraser end. Somehow there's it can recognize the eraser end, so I can sort of do the erase like a pen, like a pencil. All right. So the question is, how do we know all of these things? So the idea is, we just look at the original amount, which is $17.69, and then we start with the largest bill value in the register, right? So the largest one, at McDonald's is probably a $20 bill. Okay, so we say, nope, $17.69 is less than 20, so we won't need a $20 bill. And then we move down to the $10 bill, and then we divide 17.69 by 10 to figure out how many $10 bills we need. Now, obviously, after the division, we end up with a fractional number, because it's going to be 1.769. So we just take the floor or the integer part of it, so it becomes 1. So we now know that there's one $10 bill. Then we have $7.69 left. So that we move down to the next the next lower denomination, which is the $5 bill. So 7.69 divided by 5 has an
I believe you are 4 cents over.
I'm 4 cents over.
Yes. That total comes out to 1773.
Did I mess up the math? Because this one adds up to half a dollar. Then we have this. We got 60 cents. And then we have 65 cents. And then that would be 69 cents, right?
I guess I messed up somewhere.
Computer science people cannot do arithmetics because we rely on the computer to do it. We have good reasons not to be able to carry out basic arithmetic operations. So anyway, but I'm pretty sure all of you know how to do this, okay? So now the question is, how does this have anything to do with base conversion? Okay, but before we get there, let me just tell you how difficult making change is in the United States. Okay, because I don't know about other countries. I cannot remember the currency system in Hong Kong anymore. So I can only say that in the United States, this is actually quite challenging because you have to remember and learn a lot of things to get to this point. Okay. So what I'm going to do is to look at, the currency, the denominations in currency. So a penny is 0.01 of a basic unit, which is $1. And then the next up we have a nickel, which is, times 5 to get to, 5 cents. The next one up is a dime, okay, which is a multiplication factor of 2, and then we have a quarter. I have to chuckle because the multiplier is not even the whole number itself, because it is a 2.5 as a multiplier. And then we get a dollar bill, okay, so that's 1, and then the multiplication factor is 4. Okay, it's not even repeating yet, right? And then we have $5 bills. Remember, we are skipping $2 bills because they're not very common. So we have a $5 bill. So finally we get to see x5 again. So most people would think, okay, if you're an alien, okay, and you just landed on Earth in the United States, the logical assumption is, okay, so we repeat the cycle at this point. No, because the next one is a $10 bill, and the multiplier is a 2. And then the next one up is a $20 bill, which also has a multiplier of 2. And then you might think, oh, maybe from here on we just use a multiplier of 2. No, because the next one is a $50 bill. Yes, I find this rather amusing because now we get back to 2.5 as a multiplier, and then you go like, okay, I don't know what the next one is. The alien's gonna scream at this point if the alien had a mouth, right? It's because the next one is gonna be a multiplication by 2, and let's just say the alien is really rich, okay, has got a lot of money, and I don't even know what the next one is because I'm not that rich. Is it a $200 bill or $500 bill?
I'm pretty sure they terminate at that point.
Oh, okay. Or the store is going to look at you funny and go, like, yeah, they would just call the police. They look at your bill and go like, is that monopoly money? All right. But okay, so the focus here is just look at the multiplier. Look at this column here. There is no specific pattern to it, and yet you know how to deal with this. Okay, and that's why I said if you know how to make change in the United States, you have already learned more than what you need to do base conversion. And then you go, but wait, hold on, Tech, what do you mean by that? Okay, so let's start with another amount here. Okay, we'll say this is like, okay, let's make this $18.625. Okay, 18.625 dollars. Okay, and you want to make change, and some of you right away said, that cannot be done. But wait, hold on a second here. We are going to change the currency system here. This is tax currency system. If tech is to become a politician, this would be my platform. Binary, okay? Everything is going to be binary. That is my platform, okay? So just hold on a second here, okay? It makes a lot of sense. So we start with, the unit, which is a dollar bill. And so when you're moving up, in terms of the denomination, the next one is going to be a $2 bill, $4 bill, $8 bill, 16, 32, 64, 128, blah, blah, blah. Okay? And then we go the other way, to the fractions, okay? But it's also going to be in binary. So if multiplication by 2 is how you get to the higher values, then division by 2 is how you get to the smaller values. So we'll get to a $half, we'll get to a $quarter, and then we get to the smallest one, which is going to be, whoops, I got that wrong. Then we get to a eighth of a dollar, okay? That is the currency system. So now the question is, that looks awfully weird, and how do we do this? How do we come up with the amount of $18, $18.625? Guess what? This is easy, okay? It doesn't even have division in it, because in the U.S. currency, okay, if I specify like 91 cents, then you have to use division to figure out that there are 3 quarters in 91 cents. In this system, all you need to do is to compare. Then you don't even need to divide. There's only comparison. So what we do is we just move down. We move from, okay, I'm going to change the color of my pen. So what we do is we checked 128. Nope, we don't need that. We check 64. We don't need that. We check 32. We don't need that. We check 16. You go like, we need a 16 because 18.625 is greater than or equal to 16. So we need one of those. So now you say, what is left? Okay, what is left is $2.625 is left. Okay, and then you go up again. Okay, you say, do we need an 8? Nope. Do we need a 4? Nope. Do we need a 2? Yes. Now we have $0.625 of a dollars left. Then you move down to a 1. Nope, don't need one of those. You move down to 0.5, right? Then you go like, yep, we need one of those. And now you have 0.125 left. Then we don't need a quarter. And we do need 1/8. Then you have 0 left. Woo! That doesn't sound too bad. Right? Right?
Yes.
Yep.
Sure.
Yep. So this is why I said, it is a perspective thing, okay? Because once you relate something that relates to, that has some of the elements of base conversion, but it's actually harder, and then we just have to cast that original harder problem into something that is more structured, that is more predictable, and then we just find out that, hey, that's not too bad. So now, but we are not done with this, example yet, okay? Because we also want to, I'm going to go back to a solid line at this point. So we want to write this number and go like, but how do we specify this number, okay? There's just a whole bunch of zeros and ones. I mean, that's just odd, okay? So what we do is we just, we read the number this way, okay? In other words, this is going to be the left-hand side. This is going to be the right-hand side. The left-hand side is also called the more significant digits, and then the right-hand side is also called the less significant digits. So we go from left to right, left-hand side being the more significant digits, and then the right-hand side being the less significant digits. So we go like, oh, okay, so we got 0, 0, 0, 1, 0, 0, 1, 0, 1. Whoops. Did I mess up someplace? So after the 2 zeros, we got, okay, there we go. Okay, but wait, there's more. Okay, what do you think is the purpose of the decimal point? The decimal point is a separator. Okay, it separates the unit digit. In other words, the unit digit tells us how many ones we have from the most significant fractional unit, which in base 10 is a 0.1. How many 0.1s do we need? But then in base 2, it would be the value of half. Okay, so the point is going to be right here. Okay, this is where we draw the point. So the way we put the point in here would be right there. So this is a base 2 number. Okay, it's a base 2 number that represents exactly the same value as the base 10 number that we see here. Alright, so are there any questions about how we just did a base conversion from base 10 to base 2? Okay, well, I'm glad that it's helping. I mean, base 2 is a very, very useful base. It is simple to understand. It doesn't, things are very easy to do. Okay, division is easy to do. Addition, very easy to do. It seems odd and difficult to us because we have been poisoned by base 10 for, in my case, for a lot of decades. Okay, you guys are younger, so you're not, you have not been you have not accumulated the poison as much. But it's only because we have been using base 10 for so long that we find base 2 to be awkward. Okay, but base 2 makes a lot of sense, not only in computer science. Okay, if we want to teach addition and subtraction in elementary school, base 2 will be done like that. Okay, because the concept of adding and subtracting is actually very simple. So why did it take about a year for young children to master addition and subtraction? And then they can move on to multiplication, and then they can move on to division. So why did it take so long? Because the tables is huge when you're dealing with base 10. Okay, the multiplication table is something that we talk about a lot, but there's also an addition table and a subtraction table. Okay, how do we know that 2 minus 5 in base 10 is 7 with a borrow of 1? Because we have memorized it. Okay, but that table is large. Okay, and for a young person, memorizing that table is a lot of hard work. Okay, which I think is totally unnecessary. Okay, so that's kind of my view on the downside of using base 10. And the only reason why we're using base 10 is simple. We got 10 digits. We got 10 fingers. And that is not a good reason to choose to continue to use base 10 when there are better bases that we can use. All right, so I'm looking at the time. We are past the end of the lecture time, so we are moving into lab time. But before I close the screen share, I want to know, whether there are questions or not.
Sir?
Yeah, go ahead.
So you just put the dot after, like, for when it went into the decimal place, but in my one of my classes, when we had to convert base 10 into stuff with decimals, we had to shift it into negative or something. It was really much more complicated. Is this how we're going to be doing it, or is there a way to how do we really show that it's in that space?
We are just going to use this approach, because what the point is really doing, what the so-called decimal point, because in the case of a binary number, it really should be called a binary point. But what the point is doing is it is a separator, because we need to know where is the digit corresponding to a base to the power of 0. In other words, which digit is telling us how many ones we have. So in a base 10 number, this is the digit that tells us how many ones we have. And in base 2, this is the digit that tells us how many ones we have. So in order to put an index, so to speak, a marker, for that particular digit, convention is that we use a point to the right hand side of the digit that indicates the number of ones. It's just a convention, but we can use that convention in any base. So in base 10, we can use that convention, and then in base 2, we can use the same convention. Does that kind of explain, how I put the point in base 2, down here?
Yeah.
Okay.
Yeah. Well, I like that explanation. Thank you.
Sure, absolutely. So in today's lab, we are just going to do the NAND 2 stuff, not going to be continuing to do base conversion. But next Tuesday, we'll be doing base conversion in our lab. So basically, what I'll be doing next Tuesday is I'm going to finish all of these topics in this particular module. So it would be very helpful if you go ahead and read ahead of me, so that at least you're familiar with what we are going to be talking about. You might jot down some questions so you can ask in class, and so on and so forth. Okay, so that's kind of what I want you to do. Now, since we're moving on to the lab portion, and some people did not, get the lab done correctly, so what I might do is to demonstrate how to get it done, so that people who did not get it done correctly on Tuesday can do it again, and this time get it done correctly, because you kind of need that, I think, maybe not, to do the lab today. So I'll stay on the voice chat channel, when I kind of just go ahead and take a look at today's lab and see how much of the lab on Tuesday you will need for this lab.
Your tablet's still there.
Yeah, so you need this. Okay. And then the next page.
TAC.
Yeah.
The tablet is still 4 screen.
Oh, okay. Well, okay, let me turn that off. I need a shortcut key to do that. Does anyone know whether OBS can
Yes,
have
it
its
can.
own?
Hotkeys.
But can the hotkey be programmed to turn on and off the visibility of a source?
Yes.
Okay, cool. I'll learn how to do that. I just need to know whether it's possible or not.
And even then, if you can't, you can program it in Python.
Yep. Yeah, I'm just starting to learn Python. You guys would be laughing because, you would say, Tech, don't you already know Python? No, I have been trying to avoid learning Python. But I'm learning Python because I want to learn how to do programming in Godot, the game engine. Okay, so it does seem like we have to do that. Okay, fine. Yeah, I'm going to show you guys how to do the Nand Gate. So if you got the first lab done correctly already, hopefully you remember to save the file. So one of the good things is we are not using the lab computers anymore, because with the lab computers, if you forget to save the file or send it to yourself, I suppose you can download it from the first assignment too. So you can go back to the first assignment, go to the last question, and then click on the link, and you can download your own file back. So if yours is correct, you can just go ahead and download it. If yours is not getting a full score, so you might want to stay on the voice chat and also stay on the screen share so that I can show you how to do that. But for the rest of you, if you can just kind of move on to today's lab because you got it done already correctly on Tuesday, you can go ahead and close the screen share so that other people can get in if they need to. but I'll stay on the voice chat, also. So it's up to you guys how you want to do it. All right. So YouTube side, the YouTube side is still streaming. So for those of you who want to say, but Tech, I cannot remember what you just said 10 minutes ago. Well, you can use YouTube to kind of go back 10 minutes so that you can replay a certain portion, and then later on catch up with my current time presentation. All right.
All right. Excuse me, Professor?
Yeah.
Yeah, my lab password is not working for some reason.
Your what is not working?
The lab password.
Your
Did
lab
you copy the one that I mistakenly put up earlier?
passcode?
Sorry?
You mean the access code?
Yeah, the access code.
Is Nand Droid.
Oh, okay. All right. Thank you.
Okay. I was able to predict the future. No, it is really just a observation over the years. That's all. Alright, so I am going to start up Logisim. So if you don't need to listen to me or watch my screen, you can just either mute me, or just kind of turn off BC on Discord. So I'm not going to distract you from your lab. On the other hand, if you need this portion, then you might want to stay on so that you can redo this. I want to do this so that you can learn how to do this yourself. So instead of having me to redo everything and you just kind of copy the file, I want you at least to go through the motion so that you understand what you're doing. Alright, so we got input pins. We got 2 input pins and they need to be 8-bit wide. Okay, so the data bits here needs to be specified to an 8. Okay, and then you can move it around. There we go. And then we just do a Control D to duplicate, or you can always go to Edit and then do the duplicate from here. There we go. Now the duplication is not needed. It's just a convenient way to say, hey, I need one of those again. Okay, but if you want to just draw a single bit input pin and then make it 8-bit wide again, hey, there's nothing wrong with that. You can always do that. And then the output pin is also 8-bit wide, so we will stash the output pin here and also specify that this is going to be 8-bit wide. And I'm going to zoom out a little bit, okay, just because we got some other components that we need to specify in the circuit. And then we switch to wiring, and then we go to power. Okay, we just need one of those. We need one ground. Okay, so ground is down here, right next to power, and we just need one of those 2. Then we have to specify transistors. There are 4 transistors, 2 p-type and 2 n-type. So when you specify the transistors, you take one first, and it doesn't matter whether you draw the n-type first or the p-type first. So I'm just going to deal with the p-type first because it is by default a p-type already. So with a p-type, the source, which is where the arrow is coming from, needs to connect to power. So I can do everything in this orientation, but it's going to look very ugly. So I'm going to rotate it so that the arrow is pointing down, and that is controlled by facing. So instead of having the whole thing facing east, I want to rotate it clockwise by 90 degrees. So it's going to be pointing south, like that. So I need 2 of these. So duplicate, Control D, gets to the other one. So if you are trying to make your own circuit, so that you have a starting point for today's lab, you might want to watch the whole thing first before you go back to do it yourself. Because when you're doing it yourself and trying to watch this and listening to me at the same time, chances are you're going to get lost somewhere. Okay, so that may not be a very efficient use of your time. Okay, just gonna let me finish first, and then you go ahead and do it yourself. So with this one, I don't like it, pointing this way. Okay, so I can flip it so that the gate location is on the other side. This was totally optional. Okay, so if you don't want to do it this way, that's fine. Okay, just In the end, it is the logical connections between the ports that is important. Okay, so now we need to draw the two n-type. Okay, so we have two n-types, but the first thing I want to do is to turn one of the p-type into an n-type first. So you select the transistor, and then you go to the type, use the drop-down box to specify it is now an n-type. So the only difference is the dot is gone. Okay, the dot indicates it's the p-type transistor. The lack of a dot means it is an n-type transistor. But with an n-type transistor, the source has to connect to the lower voltage. So this arrow should not be going in from top to bottom. It should be connecting from bottom to top. So you're not going to rotate it. That is, oh yeah, you're supposed to rotate it. Sorry, I just said the wrong thing. So you're going to rotate it. Okay, so instead of facing south, we want it to face north. So we want the arrow to point from low to high. And without the bubble. So now we are ready to duplicate again, and then we just have to connect these two in series. But before doing the actual connection, I just want to place all the components to their approximate locations that we want to use these components. So now it's time to make the connections. Alright, so we'll go ahead and draw the wires to connect from these ports to the port of something else. Okay, so we go here, we stop there, connect these two, and then connect power to this one. So now here comes the fun part. Okay, so the circuit is pretty much done. However, we still have to hook up from the input pin to the gates, or to the gates of the transistors, and then we have to hook up this point to the output pin. So if you just kind of do the wiring like this, you're going to have a problem. It's going to tell you there's an incompatible width. So in the lab on Tuesday, this was kind of discussed in the instructions already. But I'm just going to verbally describe what is the deal here. Okay, so the deal is that the transistor has a bit width of 1, but the input pin has a bit width of 8. So when you make the connections, it's not going to work because there are inherently 8 individual conductors coming out of this wire, but there's only one coming into here. So Logisim says, I do not know, how to combine the 8 wires into one. So that's why it's not going to work. So what we need here is a splitter. Okay. Oh, I take it back. I take it back because there's only one input pin, not 2 input pins. There's only one input pin. It's 8-bit wide, and then we extract the least significant 2 bits to become the wires connecting to these the gates of these transistors. So what we need is a splitter. Okay, so this wire has 8-bit, it's 8-bit wide, and then we go to the splitter, which is here. So a splitter looks like this. Okay, so the input, or this end of the splitter, I'll call it the merged end of the splitter, is going to connect to this point here. So that's going to be 8-bit wide. So as soon as I make this connection, it's going to choke, because the splitter, if I click on the splitter, you can see the splitter has a bit width of only 2 instead of 8. So you should make it 8. Okay, and as soon as you do that, it's going to do something that is also wrong, because it wants to distribute all 8 bits to 2 output wires. So it's grouping bit 0 to bit 3 to one wire. It is grouping 4 to 7 to the other wire, which is not what we want. Okay, so to change that, we go to the mapping between the bits to the position of the split end. We want bit 0 to go to the top end. Yes. We want bit 1 to go to the bottom of the top end. And now it looks kind of funky, because we also want to specify that bit 2 to bit 7 do not connect. So you basically just say that these bits do not matter in our circuit, so they do not connect to anything to the split end of a splitter. So they are all none in this case. So now our splitter looks good. Logisim is not complaining anymore, and now we have to make the connections. So if I remember correctly, this one goes here, and it also goes here. And then this one goes to the other two, goes to the gate of the other two transistors. Nope. Okay, that one's fine. And this one also has to go here. There we go. Alright, so the other end is going to be exactly the reverse, because coming out of this point here, coming out of this point is one single bit, but this is a bit wide. So now we need basically, it's still a splitter, but we are reversing the direction of the splitter. So to reverse the direction of the splitter, you can just change the facing. So instead of facing east, you can make it face west, like that. And this time we also need the splitter to have a width of 8. So go ahead and specify 8 here. And once again, we have this problem. So go to the individual bits here, and then change the position of the split end that you want to connect it. So you want to bit 1. All the bits other than bit 0 do not connect to anything. So just specify none for all the other bits. Only bit 0 connects to the only split end in this case. So we want to change the fan out to 1, 2. I forgot to do that. Sorry about that. Alright, there we go. So that looks good. Not or not. Doesn't look good because now it connects everything to the one split end. So now I have to go back and re-specify that bit 1 to bit 7 do not connect to the split end at all. So these are all none. There we go. Alright. So now we move it around a little bit so that things are aligned and look good. There we go. Alright. So I believe this works. So I'm going to exercise this a little bit. Okay. If I specify a 1 and a 0, the output is a 1. If I specify this, it should also be a 1. If I specify 2 1s, the output should be a 0. Yep. So that's working. But you're not done yet. Okay. You're not done yet because you have to change the appearance. So you want to use this tool to change the appearance. You can also go to project and switch to appearance. Okay, so that would be edit circuit appearance, like this. So either way, we get you to this diagram, and that's all you need. As soon as you get to this diagram, this view, which is the packaging of the circuit, you're done. So now you just need to save the file because we're going to reuse this. But today's lab is based on this. Okay, so if you get to this point, then you're ready for today's lab. But definitely save the file, because if you don't save the file and Logisim crashes, which it does sometimes, then you have lost all your work. Okay. All right. So that should let people who did not get a full score for Tuesday's work to catch up to start on today's work. So I'm going to go back to the text channel, because while I was talking, I did not pay attention to the text channel. Okay. So let's see. So the reason why we are making the input 8-bit wide is because the tester circuit surrounding this entire thing has an 8-bit input, and that's just me kind of making a standard so that it's easier for me to build tester for other circuits. We might eventually use more of these bits, but at this point we are only using 2 of those for the input and using 1 of those for the output. Okay, I guess I accidentally used 2 input pins, but it should be just 1 input pin because it's a multi-bit input pin, so we just need to split the bits inside the input pin, and we just get 2 of those to become the actual terminals to connect to the gates of the transistors. Let's see, moving on. So the diagram in the text channel at timestamp, let me see. Yeah, at timestamp 710, that one has exactly the issue of the splitter is reversed. Okay, because oh no, I take it back. This one has a problem because the splitter is a 1-bit splitter. So the splitter itself needs to be 8-bit wide, but of the 8 bits, you extract only bit 0 to connect to the output pin. So that's the feedback for Grant at time mark 7:10 p.m. Okay, so I think all of the concerns should be addressed at this point. So I'm just gonna make one last call. Is there anything else you guys need me to demonstrate? Oh, I just scrolled down. There's a lot more stuff. Okay, never mind. Where's the design of gate 1? It's part of the question. Yeah. So Alfred has got it. Thank you, Alfred, for answering that question. Cool. Okay, so I think I'm all caught up. Unless there are specific questions about the lab on Tuesday, I am done. The NAND 2 is an earlier part where you rename main to NAND 2. How do we add gate 1? I believe that is part of the instructions in the lab, so you guys got to go slower, okay? You got to read the instructions a little bit more carefully because I believe all of that is in the instructions. Alright, so let's check that. Okay, how do we add gate 1? Okay, so oh, that's the wrong lab. So the idea is, the lab should be sufficient. There should be enough instruction in the lab for everybody to do it. So try to do this by yourself, a little bit longer before you ask questions, because it's not going to help you if you ask questions a little bit too soon. Because the idea is not to rush through the lab, but to learn from the lab. All right. Okay, so Alfred has a good question of how do we check whether the lab is done correctly or not. Let me see. Okay, so the way you test it is you feed different signals to X and Y, and then you compare what this overall circuit is doing with the operator that you have chosen. So that's kind of one way to check it, because we know what AND is supposed to do, we know what OR is supposed to do. So when you submit it, you just really have to look at gate 1 and see whether it is consistent with what you think the gate is doing, and then you check gate 2, also the same way. You'll exercise the input pins and see if the output pin is consistent for all possible test cases to the gate or to the logical operator that you have chosen. So that's kind of how you can test it. All right. How does the test work in question 4? Okay, so we are talking about this circuitry here. Okay, so that goes to, okay, so in order to answer that question, you have to watch this video here. So if you watch this video testing a circuit and how tech grades some Logisim labs, that will give you an idea of how to use Logisim and the circuit file that I have provided in order to check whether yours is working or not. But I did not provide the reference design for you, so you can only test your own circuit. but based on but you can exercise the single input test circuit and the double input test circuit by hand to make sure that it's working the way it's supposed to. All right. The first lab is not reopened. Okay, so the edit does not is not going to count. Okay, but it is needed for lab 2. No, you cannot resubmit the first lab. There we go. All right. So it looks like I don't need to keep the screen share on anymore. So I will turn off the screen share on Discord and also on YouTube, and then I'll also get out of the voice chat. But I will keep an eye on the text portion.